introduction, and thanks to the organizers for the opportunity to make this talk at this very nice conference in this very nice place. I will present the work, which is theoretical work done at Palatsky University in Olomouc. So in case you wonder where it is and what it is, so it's in the Czech Republic, but not in Prague. It's in the eastern part of the country, so it's between Slovakia, Poland, and Austria. So when traveling, I can choose between different airports. And since it's a small country, they divided the topics, and somehow Olomouc, which is a small medieval town, got optics. Well, because of some reasons that there is optical industry nearby. And then it turned to quantum optics, so there is a heritage in this. And we do lots of theory there, but as well there is some experiment. But this is a purely theoretical thing. Despite being more applied than things which were discussed in the previous days, I hope it will be still entertaining and maybe even stimulating for some. We will briefly discuss what is continuous variable quantum communication, how it's performed, what are the attacks on the phase reference from which it can suffer, besides many other things. Then I will introduce or recapitulate a single quadrature protocol that we developed a while ago, and then the extension which allows to use it for continuous variable communication without sharing a phase reference. And then we'll discuss with robustness and feasibility of the protocol briefly. So quantum communication in the continuous variable regime, most of all, is defined by the detection scheme. So we are doing homodyne detection there. So in the prepare and measure setting, Alice has a source of some quantum states, typically coherent states. More exotically, it can be squeeze states, and it brings some advantage, but this is not the story which I'm telling today. So imagine a source of coherent states, then amplitude and phase modulation, and then the states, they travel through the quantum channel to Bob, who performs the homodyne detection. So splitting on a balanced beam splitter with a local oscillator, which is a phase reference for this homodyne measurement, and then measuring the photocurrents on the output, and then subtraction scheme gives you the outcome which is proportional to the quadrature value of the signal. Yeah, so in a sense, it's not the direct measurement, yeah, when we detect photons which come straight to the detector and they either click or no click in the Geiger regime, or we can count photons, but instead we measure quadratures of the field here. The protocol was first introduced by Fred Grossans and Philippe Granger, so the group from Sorbonne. Then it was also developed for squeeze states, and then there were many other things along these lines. So yeah, basically we're dealing with the observables which are field quadratures, which are conjugate. So they are related through the uncertainty relation. So if we introduce an uncertainty of an operator, then they satisfy the Heisenberg principle. So the product of the uncertainties cannot be lower than 1, and coherent states, they are the minimum uncertainty states, so they hit unity here. And so the protocol is based on Alice modulating the state by performing the Gaussian displacement, applying random Gaussian displacement by generating 2 Gaussian random variables. So then this quantum dune travels across the phase space, yeah, and the mixture of these states individually sent by Alice is then something which is equivalent to a thermal state. So from point of view of Eve, the thing which travels through the quantum channel is a thermal state, but each time Alice and Bob, they are correlated within the uncertainty of a coherent state, so within a short noise uncertainty. Yeah, and then they perform standard procedures like basis reconciliation, error correction, parameter amplification. And so there was a great deal of progress achieved in the past decades here. So long distance implementations with the low key rates, but they are like 200-kilometer distance in super transparent fibers, or some higher key rates at shorter distances. We recently prepared a review on this. There's many things discussed there. Yeah, it's soon to appear in reviews of modern physics. Yeah, I'm very happy that Ulrich and Tony as well contributed to that, who are present there. And so if you're interested in this topic, you can refer to that. But there's certain issues for these protocols. So first of all, they suffer from losses in the channel, from the noise. So basically, while discrete variable protocols, they're kind of inherently post-selective. Yeah, if you measure the photon and the degree of freedom is not affected by the environment, then you can expect that that your channel is perfect at this moment. And when you don't measure the photon, well, you don't care. It means that that you select only the successful events. Here we have to measure all the time, and and our states are subject to losses and noise continuously. So besides issues in the channel, there can be noises in the modulation and the detection scheme. Well, we can attribute them as trusted noises, so we can deal with that. Parameter estimation is an issue, especially in the finite size regime, because we accumulate some finite statistics and we need to know what are the parameters of the channel to be able to estimate how much Eve could get. Imperfect data processing, so the mutual information between Alice and Bob, it's not the channel limit, but something below that. And one of the issues is attacks on the local oscillator. So this thing which propagates through the channel along with the signal, this phase reference, can be the subject to Eve's attack as well. In the early days, people didn't care about this, but then after some research, people realized that, well, there can be actually many things happening there. So first of all, Eve can apply local oscillator intensity attack. She can equalize signal and low intensities and or introduce a low intensity fluctuations, by this affecting the outcomes of the homodyne detection. Or she can do a wavelength attack, so she can change the wavelength of this phase reference, re-emitting the signal at a low and local oscillator at different wavelength. And this will affect the balancing of the detector here, which is of the beam splitter here, which is sensitive to wavelength. Short noise calibration attacks, by reshaping the pulses of the local oscillator to delay the detection trigger, changing polarization of the local oscillator. So all of these attacks, they affect the parameter estimation. So basically, Bob measures something different from the behavior which he would expect. So by attacking this phase reference, Eve is able to partially control Bob's measurement and impose, for example, wrong estimation of the channel noise. So by this, she increases her information, but Alice and Bob do not notice this. So all of these attacks, they lead basically to underestimation of the channel noise. There are ways to counterpart that, so countermeasures against these local oscillator attacks. So first of all, you can apply monitoring, so you can check what is the intensity, what is the wavelength, what's the polarization, or somehow restore it, which adds complexity to the setup. Another approach, which is quite popular now, is to generate local oscillator locally. And then phase lock using the pilot tones. So some bright pulses which Alice sends to Bob from time to time, which are then serving as kind of phase reference to which Bob locks his local laser system, his local oscillator. But these pilot tones can also be subject to attacks because Eve could still distinguish between signals and pilot tones. So there's, it's the patching and countermeasures against this. So the question which I started to wonder about at some point is, can we implement continuous variable QKD, or can we do quantum communication using continuous variables without a shared phase reference at all? And I was inspired by our result from a few years ago, which is the protocol which is based on a single quadrature encoding. So remember, when I was showing you the phase space distribution, this quantum dune Gaussian shape was traveling around the phase space because it was randomly displaced by two Gaussian random variables. Now, instead of displacing in these two, we can apply the modulation along one quadrature. So initially, we were just curious to see if it works, and technically can improve a little bit or simplify your setup because you need only the amplitude modulator, for example. So imagine Alice having a laser system. Then she applies one quadrature modulation. So basically, she generates kind of a saucer shape distribution in the phase space instead of this symmetrical thermal distribution, right? And then it travels through the channel. Similarly, I omit local oscillator here, so imagine this is the signal, and Bob does the homodyne detection here on his side. And the security analysis of this scheme, like many other schemes in QKD, is done through equivalence of the preparation to the entanglement-based representation. So basically, Alice has the source of entangled states. She measures one side, and then she sends it the other mode, the other side she sends to Bob. Here the peculiarity is that it's not just a two-mode squeeze vacuum, which is a standard purification of Alice's preparation in CV QKD, but we have to additionally apply squeezing operation so that we have this asymmetrical sausage on the phase space. Yeah, so this squeezing is defined very simply by minus log square root of v. Yeah, so this is the parameter of the exponent to which the quadratures are being multiplied. Yeah, so one of the quadratures gets squeezed, another gets anti-squeezed, and by this we achieve this very asymmetrical distribution. So a bit of math, but nothing scary here actually. So we can describe the covariance matrix of this two-mode state. Yeah, so starting from the symmetrical two-mode squeeze vacuum, which I guess you very well know, applying squeezing operation. Yeah, and then this state travels through the channel. Okay, so something happens along the way. The correlations are downscaled by the transmittance. There is some excess noise appearing here. Yeah, and then we use this to calculate the key rate, which is basically the information advantage that Alice and Bob have over Eve. Yeah, and the trick here is to estimate what is the Holevo bound. So what's the maximum information which is available to Eve? Yeah, so it's calculated as von Neumann entropies of this covariance matrix. Yeah, it's all very straightforward. The techniques which are very well known, but the trick here, since we don't modulated one of the quadratures, we don't know what are the correlation terms here. Yeah, because Alice puts no information here. Yeah. She modulates only x quadrature in our, well, let's assume she does it only in x. So in p quadrature, the correlations are unknown. Yeah, so we have to do something with this. Yeah, because, I mean, the variance on the output, yeah, this is what Bob measures. Yeah, he knows what is the variance in x. He knows what is the variance in p. Yeah, because this is what directly is coming to his detector. But to deduce what are the correlations, they have no data. Yeah, they have nothing to compare to on Alice's side. So we started to think how to overcome this, and well, the most straightforward way is to bound Eve by physicality constraints. Yeah, so her attack should preserve the physicality of the state which is shared between Alice and Bob, right? It's very simple condition, so it's basically extension of the Heisenberg uncertainty principle in terms of the covariance matrix. So covariance matrix after the channel plus I, the symplectic matrix, should be positive definite. The solution to that is a parabola on the phase space. Yeah, so basically we look at what are the allowed correlations for the given variance that Bob measures in the unmodulated quadrature. Yeah, and you can solve it analytically, quite simple, with the vortex defined by this point A. So on the phase space, the allowed correlations with respect to the Bob's variance, which he measures in P, form the parabola. This is, so outside of it, the states are unphysical, so you cannot do anything. Yeah. Inside this, we can calculate what is the region for security of the protocol. Yeah, and so for some values, the protocol starts to be insecure. So basically, we can calculate the key rate for the given variance of unmodulated quadrature and the given correlation in this unmodulated quadrature. It would be actually very nice if the pessimistic bound goes along the physicality region, but it didn't happen so. So in fact, we had to numerically optimize because at some point this physicality region or this security region starts to deviate from the physicality. Yeah, that's a bit annoying. So you need to apply some numerics there. But otherwise, yeah. So I mean, if we look at this cross section, then the key rate behaves monotonously with respect to the correlation in the unmodulated quadrature. But if we look at this cross section here, then we see that the key rate starts to increase at some point. Yeah, so we need really to find the optimum for Eve's attack. Yeah, so basically the security analysis involves some numerics here. And we published this with Fred Grossens a while ago, and this protocol became quite popular because, I mean, it simplifies the things a little bit. But another possible application for that is that we can use it to avoid sharing the phase reference at all. So the idea is plain simple. We take the single quadrature protocol by applying the linear modulation, so modulation along one line. But now instead of a homodyne detection, we do heterodyne, so basically a double homodyne. We generate a local oscillator locally. Yeah, we split the signal into two. So these are the two homodyne detectors in which we measure X quadrature on one detector, P quadrature on one detector, and X quadrature of another. And then, after accumulating sufficiently big data, big statistics, Bob can deduce what are the variances of the distribution that he obtained. Yeah, and then he can apply the rotation to his basis until he sees that the uncertainty in one of the quadratures is minimized. Yeah, and this is the moment where he hits the same basis alignment as was prepared by Alice. So it's all very simple, at least as the wave explanation. Yeah, so rotate the basis until you see that sausage in the phase space with the minimum uncertainty in one of the quadratures. But in practice, the things may be a little bit complicated. So I have looked at how feasible this protocol in principle can be. So the security analysis of this, yeah, it follows the same reasoning as the single quadrature modulation as I described. So it's the entanglement replacement of the source with the squeezing in one arm and Alice performing heterodyne detection, homodyne detection using her own local oscillator. So what happens if there is a basis mismatch? Yeah, because they would never restore the basis perfectly. I mean, there will be always some misalignment between Bob obtained from his statistical analysis and rotation of the basis and the basis which Alice prepared initially. So if this basis misalignment is fixed, yeah, then they would just see the reduction of their mutual information. So if we assume that, for example, Eve does it on purpose by somehow reshaping the states in the channel to play around with this basis alignment and make it with a constant shift, then it's not helpful for her because Alice and Bob would observe this as the worsening of the channel. Basically, the mutual information will drop. Yeah. A more interesting situation is when this basis mismatch will fluctuate, and this is what will likely happen. Yeah, that there will be some statistical deviations, that Bob will not be able to hit this direction perfectly, and well, assuming that there will be residual phase misalignment, Gaussian distributed or normally distributed around zero, we can see what will be the effect of such noise. Yeah, so if we apply the phase shift to our signal mode, which travels through the channel, yeah, then we can derive what will be a general two-mode covariance matrix after the phase shift. Yeah, so here we don't take the TMSV, we just study how the covariance matrix would change. Yeah, so after the phase shift and then applying, finding statistical moments of these functions of the angle theta, we can find what will be the resulting covariance matrix. Yeah, so there will be some degradation of correlation, there will be some noise appearing in the variance terms. So basically the covariance matrix would be somehow more noisy after these random phase shifts. So we can plot what will be the key rates, so how sensitive will be the protocol to those fluctuations of the basis mismatch between Alice and Bob. Yeah, and we find that depending on what's the variance on the output of the channel, so basically we look at how much the variance which Bob measures exceeds the short noise. Yeah, so how much excess noise was added in the channel on top of this short noise in the unmodulated quadrature. So depending on how much noise there is, and depending on how strong the channel, the phase mismatch fluctuations are, so without for different values of this phase noise, we can see that we can still achieve security at some like 12, 13 dB, which is not, I mean, this is the channel transmittance, not anything impressive, but still like tens of kilometers, which are potentially allowed for such protocol, which is the cost of the simplification by getting rid of the phase reference. So if we evaluate what is the maximum tolerable fluctuation of this phase mismatch with respect to the channel transmittance, depending on different amount of noise that Bob is measuring on the output of the channel, then we see how this curves. There's lots of optimization involved, so they are not maybe perfectly evaluated, but at least this gives a hint of how protocol is robust to these residual basis, fluctuating residual basis misalignments. So you see the stronger the channel attenuation, obviously the less of this phase noise we would be able to tolerate, but for some shorter distance channels, we can tolerate quite high amounts of noise. And we can compare it to what was observed in the scheme in the experiments with the local oscillator. So these ones where phase referencing was performed between the signals and the pilot tones. So they were also relying on the fact that these states, they need to have long coherence times, so that the phase drift between consecutive pulses is not too strong. So at least if we take their results, this is the phase noise that they observed. Well, it's hard to compare these protocols directly, I must admit, but at least to have a hint of what are the values that can be observed in the experiment. This is a reasonable estimate. So this is the amount of noise that they observed in this local oscillator experiments. So you can see that depending on how much noise that would be added in the channel or how much noise is still present in the setup, uncontrollable, for example, modulation noise. So depending on that noise, we can still go to some reasonably few dB distances. Well, there will be plenty of practical effects here. Yeah, you can think of spectral broadening in the fibers, for example, which would reduce the coherence times and increase this phase noise. So generally, it can be an interesting task for the experimentalists. Yeah, whether they can do it so well that this mutual coherence allows really very good alignment of the phase. But I hope, yeah, this can be stimulating. So to sum the things up. The protocol, which is independent of the shared phase reference for continuous verbal communication, was introduced here, and is based on the single quadrature encoding and basis alignment after the measurement based on the statistics of the measured ensembles. The protocol is immune to attacks on the shared phase reference. Well, that's obvious because there is no such, and it's stable without the against the residual basis mismatch at some reasonable variances of this phase noise, which would allow key distribution in fibers with standard attenuation of the distances of around 40 kilometers. By controlling the phase noise, and well, basically by improving the coherence time of the signal, the distances can potentially reach up to 70 kilometers. This was published last year. And well, this is basically all. I thank you for the attention. Obrigado pela atenção. Thank you very much. Atenção. Yeah.
Okay. Thank you very much. So,
thank you.
Time for questions. Any questions? Okay, so I'll start myself. Maybe I'm a bit confused. So your encoding is on the line,
yes,
right? So why would there still be the need for phase reference? Or I mean, because you said that there can be some. I mean, they have to check for mismatch. So couldn't they just agree on a line? Alice and Bob could agree on a line.
Yeah, but they have different phase references for their homodyne detection at the Bob side. Which does not match the one which the basis with which Alice used. Yeah, so to establish the basis, they have to rotate what was measured by Bob. Yeah, so they still have to establish some common phase reference. Yeah, and this basically suggests how to do it without sharing any phase reference pulses, local oscillator or pilot tones or something. Yeah.
Okay. Further question, Mark.
So basically, you are just rotating the data collected, not the actual experiment, right?
Yeah. Okay. You can do it on the data, which is actually a big advantage. We can do it
for sure.
In continuous variables in many things. I mean, by data processing.
So it's a post processing, right? It's like a post process.
Yes. Yeah. It's a post processing.
So I have to I would like to understand how you prove security. Like you assume there is a misalignment, or do you estimate this misalignment, or I didn't understand this. And second, okay, so if it's just post-processing, yeah, is this included in a Devetak Winter, or you have, no, I guess no, you have to compute Devetak Winter for the post-process data, or?
Yeah. Well, I mean, this post-processing is a basis rotation. Yeah, so it's equivalent to the operation which you can do on the state. Yeah, that's why it can be included in the Devitec window, right? As you still can obtain the covariance matrix of your data after the post-processing and do the calculation. And so this was just a stability check. So what happens if there is still basis misalignment between Alice and Bob, and what if it fluctuates? Yeah, so how it propagates through the covariance matrix and how it affects the key rate, basically.
More questions? I guess we still have time for a short one. No, so I'll do it myself. So is it still possible, to have these protocols with and not needing to have a phase reference, but for encodes which are not just on the line, or then there's no hope at all?
Well, here the advantage is very strong, the strong asymmetry. Yeah, the fact that we have short noise in one of the quadratures, yeah, which allows us by rotating to catch this asymmetry. If your encoding would be symmetrical, then no matter how you rotate, yeah, there will be no difference. So the key to this approach is the asymmetry of your modulation. Maybe the optimum is somewhere in between, not necessarily really the short noise limited states in one of the quadratures, but the modulation which is applied to both, but in a way which is asymmetrical. Yeah, it can increase the mutual information, but still allow Alice and Bob to use this asymmetry to align their bases. Yeah, so it maybe requires a bit more of the investigation.
Okay, so let's thank
you
Vladyslav again.
It's yours.